welcome friends. Till now we have mastered the art of differentiation. We have learnt all the different kinds of functions and their derivatives, how to differentiate functions. And now it is time to learn applications of all these derivatives. And we are going to start off with the very own tangent and normal to a particular curve. So now friends, till now we have learnt various kinds of functions, right? And we have also learned that for various kinds of functions, we have different kinds of tangents and normals, and that is what we are going to learn in this particular section, that how to find the equation of the tangent and normal for a particular point for a particular curve. Let's take an example. So let's say I have a curve over here. This is a standard curve. We don't know the equation of it. Let's just simply call this function as y is equal to f of x. So y is equal to f of x is the equation of this particular curve, right? The function is y equal to f of x. Now, on this particular curve, I have a point. Let's call this point A. And this point A has coordinates x1, y1, right? So now the stage is set. What we want is the equation of the tangent and the equation of the normal at this particular point, which lies on the curve y is equal to f of x. So basically, to put things in perspective, what we want is equation of this straight line. And as you can clearly understand, since this dotted line, which is orange in color, is touching, or so to say, is grazing this particular curve at this point A. So as you can see, this line does not intersect the curve. It just touches the curve and it touches at the point A. So this line is called the tangent, and we are going to find out the equation of this particular tangent. And on the other hand, the line which is perpendicular to this particular line is called the normal. So this line, the dotted line in pink, is called the normal to the point A which lies on this curve. Or we can say it in a better way, that this line is the normal to this curve y equal to f of x at point A, and this dotted orange line is the tangent to the curve y is equal to f of x at point A. Now friends, we know how to form the equation of a straight line, right? We have learned in the chapter of straight lines, we have learned various ways to form the equation of a straight line, and one of the most standard ways is the slope point form. So basically, if we know one point on that straight line and if we know the slope of that particular straight line, we can use the slope point form, which is nothing but y minus y1 is equal to m times x minus x1, where x1 and y1 are the x and y coordinates respectively of that particular point, and m is the slope of the line. Now, for the tangent and normal, both these lines, we have one point defined naturally because we are talking about point A. So x1, y1 are the coordinates of point A. So one point is defined, which encourages us to find out the slope of both these lines and hence find out the equation of both these lines via the slope point form. And that is what exactly we are going to do. So the equation of tangent is going to be this: y minus y1 is equal to m, the slope. Now this is where we take the help of methods of differentiation. We differentiate this particular function y is equal to f of x, which we get as dy by dx. So dy by dx is the derivative, right? Is the derivative, or you can say f dash x is the derivative of the function, and as we know, the derivative of the function is nothing but the slope of that particular tangent, right? So the slope of the tangent is nothing but dy by dx, but we need to make sure that in that dy by dx, we plug in the values of x and y as x1 and y1. We'll obviously take an example to understand this in a better way. So what goes here is, in place of slope, we will put dy by dx, which is the derivative of the function y is equal to f of x, and we have learned in the section of methods of differentiation to differentiate all various kinds of functions. But as I said, in this particular derivative, we need to make sure that we are plugging in the values of x and y as x1 and y1. So that is why we mention x1 comma y1 over here, and this indicates that in this particular dy by dx, we are plugging in x1 and y1 in place of x and y. So this takes the place of m, and after that, as we discussed, we have x minus x1. So this becomes the equation of the tangent, this particular tangent that we are looking for, to the curve y equal to f of x at the point A, which has the coordinates x1 comma y1. And after that, finding the equation of normal becomes really very easy. This is the normal, so I write that as n, and this is the tangent, so I write that as t. This is line t, this is line n. Now equation of normal, again via the slope point form, we'll have y minus y1 is equal to m. Now m is the slope of the normal. Now we need to understand that normal is nothing but the perpendicular line to the tangent, and again, with the help of the concepts from straight lines, we will use that the slope of a normal, the slope of a line perpendicular to a particular line, is the inverse reciprocal, basically negative reciprocal, so to say, of the original line. So basically, if I have m as the slope of a given line, then the slope of its perpendicular is minus 1 upon m. So in this case, if dy by dx subscript x1 comma y1 is the slope of the tangent, then the slope of the normal is the negative reciprocal of this particular thing. So what I'm going to write is minus 1 upon dy by dx bracket x1 comma y1, right? And obviously after this we are going to have x minus x1, and this forms the equation of normal for this particular curve y equal to f of x at the point A, which has coordinates x1 comma y1. And again, we need to make sure that here we are going to plug in x1 and y1 in place of x and y. That is something that we need to make sure of. Now friends, after understanding this, let's go through a few general things that we need to know and understand from this particular concept. One thing that we clearly understand, that the point A, this particular point which has its abscissa as x1 and its ordinate as y1, lies on all the three entities, the curve, the tangent and the normal, right? So what it means is x1 comma y1 will satisfy all the three things. It will satisfy the equation of this curve y equal to f of x. It will satisfy the equation of this tangent y minus y1 equal to dy by dx subscript x1 y1 into x minus x1. That's quite natural, you can see that evidently. And also this will satisfy the equation of the normal as well. Now after understanding this, a few more analytical things let's try and understand. If the tangent at a particular point to a curve is parallel to the x-axis, right? Then dy by dx subscript x1 comma y1, if at all x1 comma y1 is given specifically, and even if it is not given, you can generalize and say that dy by dx, the function of the derivative, which is indeed the slope of a particular tangent, can be equated to 0, because if a line is parallel to the x-axis, it clearly indicates that the slope m is equal to 0. So if the data in a particular question says that the tangent to a particular curve is parallel to the x-axis, and then it asks us to find something else, then we can find out dy by dx and equate it to 0. On the other hand, if the question says that the tangent is parallel to the y-axis, then I will write dy by dx is equal to infinity, right? Because if a particular line is parallel to the y-axis, then its slope is undefined, basically infinity. And when dy by dx is infinity, I can write dx by dy is 0. Just playing around with the inverse, then if dy by dx is infinity, then dx upon dy can be equated to 0. Likely, if it is given that the tangent is equally inclined to both the axes. Try and understand. If a particular line is equally inclined to both the axes, that means either theta is 45 or theta is 135, right? If a particular line is equally inclined to both the axes, then in that case you can equate dy by dx as plus or minus 1. Right? So that is one thing that is an analytical understanding to help us solve problems. On the other hand, one more thing that strikes me is if a particular line, right, makes equal intercepts on both the axes. Try and imagine a line which makes equal intercepts on both the axes. In that case, dy by dx would be only equal to minus 1, because if a line makes equal intercepts, equal positive intercepts on both the axes, then theta, the angle that it makes with the positive x-axis, will only be 135 degrees, and hence tan of 135 will be minus 1, so that you can equate dy by dx equal to minus 1. So these are a few things that we need to understand before moving to the real applications. We have understood how to form the equation of tangent and the equation of normal given the function and a particular point where we have to find equation of tangent and normal. Now let me tell you a few things, my friends. If at all a function is given and a particular point on that function is given, now I hope that finding the equation of the tangent and the equation of the normal will be pretty easy. All you have to do is differentiate this particular function, plug in x1 and y1 in place of x and y, get dy by dx for that particular thing, which is indeed the slope, and then plug in x1, y1 values and dy by dx values in this equation to get the equation of the tangent, and in this equation to get the equation of the normal. So we are not going to have standard question like this which say find the equation of the tangent, find the equation of the normal. Understandably so, these are not the kinds of question which will come in JEE. In JEE, the kind of question which are going to come will be slightly different, although they will demand you to find dy by dx, but they'll also encourage you to connect the dots. Basically, two things will be connected, which will also involve framing equations like this, but something else as well. So let's try and go through